Good day, everybody. How are you doing? Today we are going to talk about material for week 9 of Math 308. So I'll share my computer screen with you. Hypothesis test for a population mean sigma known. So we are going to do the test. Remember, hypothesis is an educated guess about the population mean. We are going to test it out. Population standard deviation is known. Sigma is Greek small s, which is population standard deviation. Perform hypothesis test with critical value method. Perform hypothesis test with the p-value method. Perform hypothesis test with the critical value method. Uh, I will go to the directly to the p-value method, which is more easy to understand and easy to do with the calculator. Okay, so let's jump directly to the hypothesis test with the p-value method, because here we can directly use the calculator. The p-value is the probability, assuming that H0 is true, of obtaining a value for the test statistic that is at least as extreme as the value actually observed. What does it mean? Remember, null hypothesis is a status quo in which we make an educated guess about the population mean. Okay, and then we collect a sample data, basically collect a sample, get the sample mean, sample standard deviation, etc. And so the null hypothesis could be something like mu is equal to some value, that is the hypothesized population mean. And the alternate hypothesis can be HA mu not equal to what we have stated in the null hypothesis. So then we compare our sample data, the sample mean to the hypothesized population mean to calculate the test statistic. So it's a difference between the sample mean and the hypothesized population mean. The whole thing, the difference is standardized or divided by the standard deviation of the sampling distribution of X bar. Okay. So the idea is to compare the sample mean to the hypothesized population mean, take that difference and divide by the standard deviation of the sampling distribution. Okay. And we will calculate a test statistic. Once we calculate the test statistic, okay, we calculate a p-value. What is a p-value? Is the probability of obtaining a test statistic as extreme as what we have assumed, what we have obtained, assuming H0 is true. Okay, so p-value is the probability of obtaining the test statistic which we have calculated, assuming H0 to be true. Okay, the smaller the p-value, the stronger the evidence against H0. Unlike the critical value, the p-value tells us exactly how unusual the test statistic is. For this reason, p-values are more often used in practice, especially when technology is used to conduct a hypothesis test. Online coaching program is supposed to increase the mean SAT scores to greater than 530. So your alternate or test hypothesis H1 is colon mu greater than 530. Your null hypothesis H sub 0 colon mu equal to 530. Assume that 100 students are randomly chosen to participate in the program and the mean score X bar is 562. Remember, I told you have to compare the sample mean 562 to the hypothesized population mean, which is 530. So 562 minus 530 is 32. Now you have to standardize that difference or divide that difference by the standard deviation of the probability distribution of X bar. The population standard deviation is known to be sigma equal to 116. So the standard deviation of the sampling distribution of the probability distribution of X bar will be sigma divided by square root of n, which is 116 divided by square root of 100, which is 116 divided by 10, which is 11.6. So that is the standard deviation of the probability distribution of X bar. So we take the difference between the sample mean, which is 562, from the hypothesized population mean, which is 530. 562 minus 530 is 32. Then we'll divide it by 11.6, which is the standard deviation of the sampling distribution. And we will get our test statistic. Basically, the test statistic tells us how far away the sample mean is from the hypothesized population mean in terms of standard deviation of the sampling distribution. So this is a calculation. So we can do the same thing in our calculator. So stat, we highlight test on the top row, then z-test. Why z-test? Because we know the population standard deviation. And the sample size is also greater than 30, which is 100. So z-test number one selected. First line input should be on stats because we know the summary stats. Mu0 is the hypothesized population mean, which is 530 in this case. Sigma, population standard deviation, is 116. Sample mean X bar is 562. N, sample size is 100. And our alternate is mu greater than 530. 530 is the hypothesized population mean. So in the fifth line, we bring the cursor or the black rectangle on greater than mu0 and hit enter. Then we will calculate. So we will calculate the test statistic. Also, we'll get the p-value, which is the probability value of getting a test statistic as extreme as what we have obtained, assuming H0 to be true. We will compare that probability value to alpha value. Okay. So hit enter, bring the cursor on calculate, let it flash on calculate, and then hit enter. So our test statistic z is equal to 2.7586. The p-value is 0.0029. Now we compare that p-value with the alpha value. So p-value, remember, is the probability of obtaining a test statistic as extreme as 2.7586. Now alpha is the level of significance. Usually it is kept at 0.05. So what is level of significance? It's a maximum probability of making a wrong decision of rejecting H0 when it is true. That means we should not have rejected H0, but we are still rejecting H0. So if we do the experiment 100 times, 5 out of 100 times we take a wrong decision. That is the risk we are taking. Okay, so we will compare the probability value, the p-value 0.0029 with alpha level of significance, which I said usually it's kept at 0.05. So in this case, p is less than alpha. Okay, the decision in this case is to reject H0 and to support HA. We state that at alpha equal to 0.05, there is enough evidence to support HA, and we reject the null hypothesis. Okay. Okay. P-value, we will not worry about this. Which provides a stronger evidence against H0, a p-value of 0.05 or a p-value of 0.5. Remember, the smaller the p-value, the stronger is the evidence against H0. Part B, a test is made of H0 colon mu equal to 30 versus H1 mu less than 30. The test statistic is Z equal to minus 1.28. So the p-value will be the area to the left of Z equal to minus 1.28 in the standard normal curve. So to find that area, we do second verse, and then we go to number 3 in norm. Sorry, we did a mistake. Second verse. Okay, let's clear everything. Second verse, we go to actually normal CDF, number 2, because we know the Z, we want the area to the left of that Z. Second verse, number 2, hit enter. The lower is already minus 1 E99. What does it mean? A very small value in the left, a very small negative number on the left. That means negative infinity. Minus 1 E99. Again, E stands for 10. That is minus 1 followed by 99 zeros. What is my upper? My upper is where I'm stopping. The minus sign next to enter, 1.28. So the lower is minus infinity, upper is minus 1.28. So we'll get all the area starting from minus infinity to minus 1.28. Mu is 0 because standard normal curve, sigma is 1, and pest twice, enter twice. And the answer is 0.10027, which they rounded to 0.1003. Okay, this p-value is greater than alpha. Usually alpha is 0.05. If p-value is greater than alpha, the decision is do not reject H0. And we say at alpha equal to 0.05, there is not enough evidence to support the alternate. Okay. So they're talking about the same thing which I just talked about. We have seen that the smaller the p-value, the stronger is the evidence against H0. Therefore, to make a decision to reject H0 when using the p-value method, we choose a significance level alpha between 0 and 1, usually 0.05. Remember, significance level is the maximum probability of rejecting H0 when it is true. That means we should not have rejected, but we made the wrong decision. Compute the p-value. If p is less equal to alpha, what is the p-value? Is the probability of obtaining a test statistic as extreme as what we have obtained, assuming H0 to be true. If p is less equal to alpha, reject H0. If p is greater than alpha, do not reject H0. If p less equal to alpha, we say H0 is rejected at the alpha level, or the result is statistically significant at the alpha level. Suppose the p-value of a hypothesis test is 0.0122. Do you reject H0 at the alpha equal to 0.05? Compare p with alpha. P is less than alpha. Therefore, we reject H0 at alpha equal to 0.05. Is the result significant at alpha equal to 0.01? Compare now the p with alpha. P is greater than alpha. So decision is at alpha equal to 0.05. Do not reject H0. Okay. We move on. Okay, how the p-value is calculated. If it's a left tail test, p-value is the area to the left of the test statistic under the standard normal curve, as in the first picture. If it is a right tail test, remember the alternate hypothesis tells you which direction the test go. If mu is greater than mu0, it's a right tail test. That means the test statistic falls in the right test, and the p-value is the area to the right of the test statistic under the standard normal curve. And if it is a two-tailed test, remember two-tailed test, the alternate hypothesis is not equal to, we calculate a z-value. If the z-value is in the right tail, calculate the area to the right of that z and multiply it by 2. Okay. So let's do this problem. The mean height of an adult man in the United States is 69.7 inches with a standard deviation of 3 inches. A sociologist believes that taller men should be maybe more likely to be promoted so that the mean height of male executives may be greater than the mean height of the entire male population. A simple random sample of 100 male executives has a mean height of 69.9 inches. Assume that the standard deviation of male executive heights is sigma equal to 3. Can we conclude that the male executives are taller on the average than the general population at alpha equal to 0.05? So the null hypothesis is mu equal to 69.7 and the alternate is mu greater than 69.7. So we go to stat, test, and z-test. Again, we are using z-test because we know the population standard deviation. Input is on stats. Mu0 is the hypothesized population mean, is 69.7. Sigma population standard deviation is given as 3. Sample mean is 69.9. Sample size n is 100. What is my alternate? Greater than mu0. So bring it on greater than mu0 and hit enter. And then we go to calculate. We'll calculate the test statistic, then we'll look at the p-value and compare with alpha. Test statistic z is equal to 0.667 and p-value is 0.25249. So p-value is greater than alpha. So the decision is failed to reject H0. And we state at alpha equal to 0.05. There is not enough evidence to support the alternate hypothesis. Okay. At a large company, the attitudes of workers are measured with standardized tests. The mean score over all employees was 74 with a standard deviation sigma is equal to 8. Some time ago, the company adopted a policy of telecommuting, allowing work from home. After the policy had been in place for some time, a random sample of 80 workers was given the test to see if their mean level of satisfaction had changed. Didn't say whether it is increased or decreased. The sample mean was 76. Assume the standard deviation is still sigma equal to 8. Can we conclude that the mean level of satisfaction is different since the policy change at alpha equal to 0.05 level? So the null hypothesis mu equal to 74, alternate mu not equal to 74. So stat test, and we go to number one, Z test, input on stats, mu 0, hypothesized population mean is 74, sigma is 8, X bar is sample mean is 76 given in the problem. Sample size n is 80 and the alternate is not equal to. So bring it this time, the cursor on not equal to mu 0, which is the first option in the fifth line, and hit enter. And then we'll calculate the test statistic, get a p-value, and compare that p-value with alpha equal to 0.05. So z is equal to 2.236 and the p-value is 0.025, which is less than alpha equal to 0.05. So therefore decision is to reject 80, and at alpha equal to 0.05, there is enough evidence to support the alternate hypothesis, mu not equal to 74. Okay. So how to do with technology, stat test and z test. And then if we have the summary stats, then we highlight stats and input the data and select the alternate hypothesis and then calculate. So we have already done this, we'll not do it. We have already done this also. A social scientist suspects that the mean number of years of education mu for adults in certain large city is greater than 12 years. So mu greater than 12. She will test the null hypothesis, null mu equal to 12 against the alternate hypothesis H1 mu greater than 12. She surveys a random sample of 100 adults and finds that the sample mean of years is X bar equal to 12.98. Assume that the standard deviation for the number of years of education is sigma equal to 3. Find and interpret the p-value. Is H0 rejected at the 0.01 level at alpha equal to 0.01? If so, state a conclusion. So stat, test, highlight test, and then go to number one, Z test. Input on stats, because we know the summary stats, or hypothesized population mean. Remember, mu 0 is always the hypothesized population mean, is 12. Sigma is given as 3. Sample mean is 12.98. Sample size n is 100. Alternate is greater than mu 0. So bring it on greater than mu 0. Bring the cursor on greater than mu 0 and hit enter. And then we go down to calculate and hit enter. So the test statistic is 3.267. The p-value, okay, the p-value is 5.44, cannot be greater than 1. So there is a e at the end, e minus 4. That means the first number 5 is at the fourth place after the decimal. So p-value is 0.0005. Compare this p-value with the alpha value. P is less than alpha. Therefore, decision reject 80, and we state at alpha equal to 0.01. There is enough evidence to support the alternate hypothesis that mu greater than 12. Okay. Okay, let's go ahead with the next one. Okay. Hypothesis test for population means sigma unknown. Previously, sigma was known, population standard deviation was known. This one, population standard deviation is unknown. Okay. So again, we will refer just to the calculator once. Okay. Test hypothesis about a mean using the p-value method, TI-84 plus. In a hypothesis test, we calculate a statistic such as X bar and compare it to the value in the null hypothesis, which is the hypothesized population mean mu zero. If the difference is large, then it is less likely to be due to chance, and H0 is less likely to be true. Otherwise, a small difference may be due to the chance and H0 may well be true. The question is how big should the difference be before we reject H0? And it's just like before, we compare X bar to the sample mean to the hypothesized population mean, take that difference divided by the standard deviation of the sampling distribution, which if we had known population standard deviation will be sigma divided by square root of n. Here it will be S divided by square root of n, as you will see. So we will do the p-value method. Okay. In a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was X bar 2.2 kilograms, with a sample standard deviation of S equal to 6.1 kilogram. How strong is the evidence that people who adhere to their diet will lose weight? Lose weight, okay? If we know the population standard deviation sigma, we would be able to compute the z-score, z-statistic, okay, which is X bar minus mu divided by population standard deviation divided by square root of n. The term in the denominator, sigma divided by square root of n, is the sampling distribution, which is the probability distribution of the sample mean, its standard deviation. However, in this example, as is usually the case, we do not know the population standard deviation. To proceed, we replace sigma in the denominator by S. S is the sample standard deviation. And we use a test statistic of T instead of Z. So T is again comparing the sample mean to the hypothesized population mean divided by standard deviation of the sampling distribution, which this time is S divided by square root of n. T also depends on the sample size, which is given by degrees of freedom, which is sample size minus 1. Okay. So here is a comparison of the top curve. The solid curve is always the Z curve, and the dotted curves are the T curve. So the first one on the top is 1 degree of freedom. That means sample size is 2. You notice the T curve is much stouter, shorter in height and wider tails at the two ends than the Z curve on the top. Then you increase the degrees of freedom to 4, the second one. Sample size is 5. Here the T curve is still a little shorter than the Z curve, but still it's approaching the Z curve. Then you further increase the degrees of freedom to 10 from 4, which means sample size has now increased from 5 to 11. Remember, sample size is 1 plus degree of freedom. And now you see all the T curve and the Z curve are almost lined one on top of other. So what is the message from here? As you increase the sample size, the T curve approaches the Z curve. Okay. So here is the test we are going to do on that previous example. We want to see if people have lost weight. So our null hypothesis mu equal to 0. That means they have not lost any weight. And our alternate hypothesis is mu greater than 0. So we put our calculator on, stat, highlight test. This time we are going to do a t-test instead of z-test. The reason is we do not know the population standard deviation. We only know the sample standard deviation S, which is 6.1. So we go down to number 2, which is t-test, and hit enter. Input should be again flashing on stats because we know the summary stats. Mu0 is the hypothesized population mean, which is 0 in this case. Sample mean X bar is 2.2. Sample standard deviation Sx is 6.1. Sample size n is 76, all given in the problem statement. What is my alternate? Greater than mu0. So bring the cursor on greater than mu0 and we calculate. So we will, just like before, we will calculate a test statistic, which this time is t, because we know only the sample standard deviation, and we will compare the p-value. We'll get the p-value, compare the p-value with the alpha. Usually alpha is 0.05 if it is not given in the problem statement. So let's calculate. The test statistic is 3.144. the p-value is 0.0011. So if we compare this p-value with an assumed alpha value of 0.01, p is less than alpha. The decision is to reject H0, and we state at alpha equal to 0.05. There is enough evidence to support the alternate, that is mu greater than 0. Okay. So choose a significance level between alpha between 0 and 1 is usually 0.05. Compute the p-value. If p is less equal to alpha, reject H0. If p greater than alpha, do not reject H0. The assumptions for performing a hypothesis test about mu and sigma when sigma is not known are: we have a simple random sample size is large, n greater than 30, or the population is approximately known. And we go to stat test, then we go down to t-test, which is number 2 selected, and then this screen opens up. Usually we know the summary stats, then we put the cursor in the first line on stats and enter the sample data that we know. Okay, we already did this test, so we will not get into it. Okay, let's do this problem. Generic drugs are lower cost substitutes for brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The US Food and Drug Administration is now supervising the testing of a new generic ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square centimeter of the screen. As part of the testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed into the skin is measured. The amounts in micrograms are given. How strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? So our null hypothesis mu equal to 3.5 micrograms. Alternate is H1 colon mu not equal to 3.5. Notice we have only 7 data points, and we were not told that the sample came from a normal distribution. So we have to check out that these numbers in the sample came from a bell-shaped distribution. And the only way to do that is to make a box plot and see that we do not have any outliers in the data. How do we do that? First, we press the second button on the top left, then plus on top of enter, then number 4, which is clear all list. Hit enter, done. Then stat button 1, enter the data in L1, which is 2.6, 3.2, 2.1, 3, 3.1, 2.9, and 3.7. So we have entered the data in L1. Now we want to make a box plot out of it. Okay. Remember, box plot, the box consists of the left boundary of the box is Q1, the right boundary is Q3. We join them by 2 horizontal lines, and then there is another vertical line in the middle of the box or somewhere in the box. This is Q2 or the median. And then there are 2 tails on the 2 left side. The left tail is not called a tail, it's called a whisker. The left whisker extends to the minimum value, and the right whisker extends to the maximum value if there is no outlier. So we press the second button after this. So after we have entered 3.7, hit enter. No, 3.7. Okay, hit enter. Okay, then press the second button and y equal to. Second button on the top left, and then on top of that is y equal to. Press number 1. Yeah, it is on. The first line should be flashing on, and then you go to the 4th type of chart. This is a modified box plot which will show us if there is any outlier. So first line is on, second line type, we bring the cursor on the 4th type of chart and hit enter. Okay, then we press the zoom button, which is in the top row of key, 3rd key is zoom button. Zoom and then 9. And we get a nice box plot. Okay, nice box plot without any outliers on the left or on the right. Okay. They did a dot plot. You can do a dot plot with our calculator. We have to do a box plot. There are no outliers on the left or on the right. If there is an outlier, it would have been shown separate from the box. plot. No, this is not true on the left, not true on the right of the box also. The left whisker ends at the lowest value, the right whisker ends at the maximum value. So now we can do a t-test. Okay. So stat, test, and we scroll down to number 2, t-test. Now the input, the first line should be on data. So bring the cursor with the left cursor key on data and hit enter. Okay. So what is your hypothesized population mean is 3.5 mu 0. List is L1, frequency is 1. What is the alternate hypothesis? Part of the, how strong is the mean absorbed differs from. So it is not equal to mu 0. Bring it on not equal to mu 0, which is the first option, and then calculate. So we calculate a test statistic of minus 2.95 and a p-value of 0.0255. So compare that p-value with alpha of 0.01. P-value is greater than alpha. So decision is fail to reject 80. And we state at alpha equal to 0.01. There is not enough evidence to support the alternate which states mu not equal to 3.5. Okay. So fail to reject or we do not reject alpha. Same decision as I told you. Okay. So let's do this one. The Russell 2000 is a group of 2000 small company stock. On a recent day, a random sample of 35 of these stocks had a mean price of 26.89 with a standard deviation of 23.41. A stock market analyst predicted that the mean price of all 2000 stocks would be 25. Can you conclude that the mean price differs from 25? So null hypothesis mu equal to 25, alternate H1 colon mu not equal to 25. So stat, test, and we will use a t-test because we do not know the population standard deviation. Okay. So number 2 is a t-test. Now the input should be on stats because we know the summary stats of the sample. Okay. Mu 0. Mu 0 is what we are comparing to the the hypothesized population mean, which is 25. What is the sample mean? Sample mean is 26.89. SX sample standard deviation is 23.41. N sample size is, what is the sample size? 35. So N is 35. Notice the sample size is 35, which is greater than 30. So we can assume that the sample came from a population which is approximately normal or bell-shaped. Okay, when sample size is greater than 30, we can do that assumption. Now my alternate is still not equal to mu 0 and I calculate. So I calculate a test statistic, get a p-value, compare the p-value with the alpha value. So the test statistic is 0.4776 and the p-value is 0.636, which is greater than alpha equal to 0.05. Therefore, the decision is do not reject 80. And we state at alpha equal to 0.05, there is not enough evidence to support the alternate hypothesis. Okay. We will not do the critical values, so just jump through this. Relationship between hypothesis test and confidence interval. Suppose that we test the hypothesis mu equal, null hypothesis mu equal to 3.5 versus H1 mu not equal to 3.5. Obtain the p-value of 0.0256. Since p is less than 0.05, H0 is rejected at the 0.05 level. Informally, this says that the mean value mu 3.5 is not possible, is not a plausible mu value. Another way to express this information is to through a confidence level in interval. If we construct a 95, remember a level of significance is 0.05. So our confidence level, that is the maximum risk we are taking in making a wrong decision of rejecting H0 when it is true. So what is our confidence level is 1 minus alpha, 1 minus 0.05, which is 0.95. And if we do the calculation, we find that the mu 95% confidence interval for mu is between 2.48 and 3.40. Notice the lower end is 3.48, the upper end is 3.4. 3.5 is outside this interval. Hence, we can safely say that we reject the null hypothesis. Note that this interval does not contain the null hypothesis value of 3.5. The confidence interval for mu contains all the plausible values of mu. Because 3.5 is not in the confidence interval, 3.5 is not a plausible value for mu. This is a relationship between alpha and the probability of error. Recall, recall that a type 1 error occurs if we reject H0 when it is true, and a type 2 error occurs when we fail to reject H0 if H0 is false. We would like to make the probability of both of these errors small. The probability of type 1 error is equal to the significance level, which is denoted by alpha, which is Greek small a. In other words, we perform our test at a significance level of alpha equal to 0.05, and the probability of making a type 1 error is 0.05 because alpha is the probability of type 1 error. Why don't we always choose a small value of alpha? The reason is that smaller a value we choose for alpha, the larger the value of beta, which is the probability of making a type 2 error. In general, making a type 1 error is more serious than making a type 2 error, which is why a suitable value of alpha is chosen before the test is performed. And Charlie will perform hypothesis test at alpha equal to 0.05. Felice will perform the same test at alpha equal to 0.01. If H0 is true, who has a greater probability of making a type 1 error? Type 1 error means reject H0 when it is true. So I would say Charlie, okay? And if H0 is false, who has a greater probability of making a type 2 error? Failing to reject H0 when H0 is false is Felice, okay? We will report the p-values because p-value is allows people to make their own conclusion. That's what all this is saying. And we will also report the test statistic. Distinguish between statistical significance and practical significance. What this slide says that a result may be statistically significant, but it may not be practically significant. So statistical significance is different from practical significance. Okay, so we will stop here today. If you have any question, please shoot me an email. I'll get back to you as soon as possible. I'm coming back next time with next week's presentation. Take care. Have a nice day. See you